put the big picture together in this video, and we're going to be talking about how we can easily sketch polynomial functions by being able to determine things like zeros and multiplicity and also end behavior, okay? And so what we're going to do is this 5-step process that is provided here. But basically what I want to do is kind of put it in a nutshell. What we'll always do is we'll determine the end behavior of our graphs, like whether or not we'll rise or fall on the left and right. But then from there we'll just find all of our x-intercepts, all of our y-intercepts, and then I'm going to skip down to letter E here because that's kind of the next pertinent step. We're basically just going to start plugging in extra x values to find more y values on our graph. And the neat thing about it is we're only going to really want to find extra x values around our x-intercepts because on the outside of those, our graph is either going to climb or fall pretty steeply. And so step D, I didn't mean to neglect step D here, but step D is kind of like, if you ask me, an extra step for you to check whether or not we have symmetry on our graph. So where it says determine whether the graph has y-axis symmetry or origin symmetry, what we're basically checking for is our function even? Recall that an even function would be any function that when we plug in a negative x for all of our x values, we get the same thing, okay? And origin symmetry would be a fancy way of saying that it's odd, or when we plug in a negative x everywhere we see an x in our function, we get the exact opposite of what we started with. It would be an easy way for us to check to see if our graph has any symmetry or not. Okay, and so let's go ahead and take a look at just kind of putting one of these together. I kind of want to work through this as efficiently as possible. So number 41 here, we have f of x is this third-degree cubic function here that's already in standard form. So with respect to letter A here, I'm going to write, this is 41. I suppose we could write letter A. What we want to do is we want to determine the end behavior. So using our leading coefficient test, first of all, let's look at our leading coefficient. We have a positive 1 for a leading coefficient. So remember, suppose if you have a positive leading coefficient, does that tell us about the left or about the right-hand behavior of our graph? And what we want to remember is that it tells us, I hope you said, about the right-hand behavior of our graph. So because we have a positive leading coefficient, I instantly know that my graph is going to rise on the right, and also because my degree is odd. Think about how the left-hand behavior compares to the right-hand behavior. If your degree is odd, it would have to behave differently. And so we would have to fall on the left. So I always recommend that once you find these things out, let's go put them on our graphs. Matter of fact, I'm going to put down on the left here and up on the right. Now, just to be clear, I just put those there as a guide. Okay, it doesn't mean that your graph actually goes through those points. I just kind of tend to put these up and down things in corners. So for letter B here, what we're asked to do is, of course, find the x-intercepts. And x-intercepts, that's another way of asking for the zeros or the roots. And so whenever we want to find an x-intercept, remember that what we're doing is we're taking our y value here and we're setting it equal to 0. So if f of x is x cubed plus 2x squared minus x minus 2, then we get this here where it looks like we're going to have to solve this by factoring, of course. But because I have 4 terms, I hope you recognize that we want to group our terms here. It would be our factoring method that we would choose to use. So I'll group my first two. I have to keep this negative on the third term there, so we'll put a plus in between, and then we'll throw that negative in here with my x and my 2. So looking at this, we want to solve this by factoring. Now I'll switch back to blue. 0 is equal to, I suppose we could factor out an x squared here. We get left with an x plus a 2. And because we want factoring to work here and grouping to work, we want this to have the same thing left over as this right here. So it is important that you guys, we factor out a negative 1. That would switch our signs over to x plus 2. Now I can see that both of these terms have an x plus 2 in common. So we still have 0, but 0 is equal to x plus 2 times that x squared minus 1 that was left over. And the neat thing about this even is that we can keep factoring it. That's what I want to do here. When we get to our final factored form, because we had a difference of squares, we get x minus 1, x plus 1. So looking at all of these, this is kind of a neat thing. They're all factored. And because I would set each of these factors equal to 0 and solve them, what I'm going to find out very quickly is that I tend to just get the numbers that are the opposites of what I have in here. If it's just 1x plus or minus some number, okay? If there's a number that's a coefficient of x like 2 or 3 or negative 8, you would actually have to set the factor equal to 0 and solve it. But because here we can see easily I'm going to get negative 2, negative 1, and positive 1, I'm going to write these here. And one thing that I want to make sure that you know is this. We should always state the multiplicity at these zeros. And because they each occurred once, okay, what I'm going to tell you is we tend not to write multiplicity if it's just 1. That is, we just assume everybody understands I mean that it happened one time unless I tell you it had a multiplicity otherwise. So because each of these have a multiplicity of 1, what we know is that it's going to cross at each. Just want to make sure we make that note here. So if letter B is to find the x-intercepts or the zeros, then letter C here is asking us to find something that's pretty natural. Let me switch back to my pen tool here. But it's asking us to find the y-intercepts. Well, how do I find a y-intercept? Well, just to be clear on this, we plug in 0 for x. And the neat thing about this is, and I'm only going to have to show this one time, is when I plug in 0 for x, at least with polynomial functions, what you're going to find is anything with a 0, or with an x rather, it drops out. So do I always get the constant term when I plug in 0 for x? And the answer is always, always. The y-intercept is always going to be the constant term. So because I have my x-intercepts and because I have my y-intercept, I don't know what's stopping us here. We should just go put these on the graph. So I know that it hits the x-axis at -2, okay, -1 and 1, and I know that it hits my y-axis at -2, which for right now at least I'm going to call that 0, -2. So step D, I actually do want to carry out step D here. We were given a function f of x, and we want to test this to see whether it has symmetry. In other words, test it to see if it's even or odd. And so recall from our days of testing for even and odd functions, we plug in everywhere a -x where we see an x. As a matter of fact, it would look exactly like this. Now, what I want you to understand is that we can do this without showing our work. We can do this just by mathematical reasoning, and that reasoning is this. Anything with an odd exponent, when we raise a negative base to an odd exponent, you're actually going to get a negative thing. So here I would get -x³, whereas here I would square my -x² first, which would make this a +x². So in other words, I get a +2x². This term did not change its sign. When I get this, an odd exponent, a negative base to an odd exponent is negative, but I have a negative, which makes it a positive. I get this right here, and then my 2 is not affected. So essentially, f of -x, we get this right here. What I want you to see is that the only terms that change their signs, okay, are the terms that have odd exponents on them. And so you certainly have my permission to just say f of -x would be the same function I get, but we'll switch the sign on these two terms right here because they have odd exponents on them. And that's what we did. So the question is, do I get the exact same as what I started with? And in this case, this is definitely not the same thing as what we started with up here. And do I get the exact opposite of what I started with? Well, I do get a -x³, but this 2x² is exactly the same as it was, so this isn't the exact opposite. So we would just say no symmetry. It's not going to have symmetry over the y-axis, like say a parent function of a parabola or maybe absolute value graph would, okay? And it's not going to have symmetry over the origin, like maybe a cubic graph would. So we did want to check for this, but basically, again, hey, end behavior, find the x-intercepts, find the y-intercept. After this, all we're going to be doing is tabling values. So for letter E here, we'll put this in here. It says, hey, if necessary, and believe me, it's necessary, find a few additional points and graph the function. Use the maximum number of turning points to check whether it's drawn correctly. So we'll visit this turning points here in just a moment. What I'm more concerned with is what x values should I put in my table? It's not like I'm super excited and I want to plug in a bunch of them. Basically, what I want you to see is that a graph is only ever going to be interesting around its zeros, because outside of this range, well, on the right, it's just going to keep going up, and on the left, it's just going to keep going down. So what would this look like if I had a graph that crosses, starts down, falling on the left, comes up and crosses at each 3 of these, and then comes up again? I could see that I'm going to get this this shape right here. So if I want to know what it does, here's our job. We're going to plug in an x value to the left of and to the right of, that's right, every single 0. So because my 0 here is at -2, I'm going to plug in -3 into my table. Because my zeros here are at -3 and -2, I hate to be the bearer, or -1 and -2, I hate to be the bearer of bad news, but we're going to have to plug in -1.5. And because I've already plugged in 0, or at least I found the y-intercept, I wouldn't have to do that one, but I would have to plug in 2. So it seems that we only need, necessity here wise, 3 of these values. So what I'm going to tell you is I want you to be using your graphing calculator on this, or a calculator. You have to bear with me while I get my calculator open, but I do just want to show you a few things here when we plug these values into our function. So first things first, we're going to plug in -3. What that would mean is, of course, everywhere in my function I see an x, I'm going to plug in a -3. So I'm kind of looking off this function up here. But if I plug in a -3 everywhere, the fact is you want to use parentheses around this. And we'd say -3 to the third power. So we use our caret key to the third. And we'd say plus 2, now in parentheses, -3, and we'll square that. Then we'd say minus in parentheses and -3 in parentheses, minus 2, and then we'll just hit enter. It looks like we get a -8 here. Okay. So likewise, what I want you to try now is this. If we hit second enter, this is pretty neat. It actually goes back and retypes in everything that you had in there before. So instead of having to type it in again, what I can go do is actually type over my -3 here 1.5, and it's a -1.5. So what we're going to do is this. I'm going to type in -1 and I'm going to stop. And what I want you to see is when you use a TI, when you type something in, it just deletes over what you were writing before. So once I've deleted over the -3 and put a -1, what I want to do now is right behind delete it says INS or insert. I'm going to hit second, okay, see how it shifts as an up arrow, and then insert. And my cursor changes. Instead of a flashing box, I get a flashing bottom line here, and anything on top of our cursor right now is going to shift to the right. So if I hit 0.5, all of a sudden everybody was bumped. So let's do this again here. I'm going to hit, I suppose, -1. So -1, and then we'll insert the 0.5, and then I'll go one more step here. So the talking, man, that took way more than just retyping it. But you know, once I know how to do this, and then insert 0.5, it'll be a little bit more quick for us here. So we get this, about 0.625. So we get 0.625. Okay, and that's at -1.5 there. And then at 2 here, let's plug in 2. I'm not keen on typing all this in again, so I'll hit second enter. And this time I'll go back up here, and I will put 2, and then I will hit delete, delete, delete to get all that out. So we would say this. Oops. Okay, so we'll hit 2, delete, 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 and then we'll come over here and hit 2, delete, delete, delete. And then I'll hit enter again and we get 12. So the fact of the matter is this. I always want you looking at your y values here in your table because we may or may not need to change the scale of our y-axis. So because I notice that I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 notch marks, I'm not going to be able to fit 12 here very easily, then we may want to change this so that instead we're going by 2s. So if that's the case, here's what I want to see you write. I want to say that our y scale, I'll put this in red, y scale is 2. And the only reason we decided to switch this is to be able to fit all of these points on here. So the annoying fact is going to be this. You're going to have to move your former y-intercept up to here if we're going by 2s. So if you're not going to tell me your y scale is 2, the other way to do this is just go up, say maybe like 5 notch marks and say this is 10. Go up another 5 and say, hey, you know, this is 20. Either way, you got to label your scale here. Our x scale happens to be just by 1, so that's like 5. So now graphing what we have, it looks like the only points I need to put on are -3, -8. So we'll go left 3, we'll go down 1, 2, 3, 4 notch marks since we want to go -3, -8, and we're going by 2s on our y-axis. -1.5, 0.625, here's all you care about. If this is 2, 0.625 is like a little bit less than halfway up. It's above the x-axis. That's all we really care about. And then 2, 12, we'd go over 2 and up to 12 here. It would look like this. So the question is, how would this graph look if we know that it comes up from the bottom here on the left? It is rising from a falling position and then comes back up again. We could see that we would get a polynomial function that looks like this. So we can clearly see that it crossed at each of our zeros here. It fell on the left, rose on the right, okay? And we had something that I suppose had no symmetry, okay? So the last thing I want to mention here is turning points. What do we mean by a turning point? Now this is up until now something we've not talked about, but this graph here, a turning point occurs wherever we go from increasing to decreasing or decreasing to increasing. And I count 1 here and then 2 here. And so with respect to turning points, one thing that I want to make sure that we record is this. The number of turning points, or the maximum number of turning points a graph can have, is always 1 less than the degree n. So we're going to insert this here. We say with respect to turning points. The max number of turning points that a polynomial function can have is always n minus 1, where n is the degree of the function. So you'll notice that the degree of our function last time was 3. It was a third degree function. So we could have at most 2 turning points. That's going to be a helpful thing to know as we sketch these graphs here. So what I want to do is I want to go through one more with you here. I'm going to talk a lot less on this one, but 43, let's take a look at it. 43 is x to the 4th minus 9x squared. So as we take a look at it, 43, we have f of x equals x to the 4th minus 9x squared. Let's go through this one a little bit more quickly on this one. So starting with end behavior, what would our right side behavior be if we have a positive leading coefficient? So because it is positive, right, we'd have rising. And because our degree is even, well, it'd have to be the same on the left. With respect to letter B here, well, letter B says go find the x-intercepts. So of course what we're going to do is we're going to plug in 0 for y, and we're going to solve this by typically factoring. So I definitely noticed that we have a common factor here. I hope you noticed that we get the same factor twice, x squared, and we get left with an x squared minus 9, which in and of itself is also factorable as a difference of squares. So it factors into our conjugate pairs here. And so looking at this here, I suppose we would say that now that this is completely factored, we could set each of these equal to 0 and solve it, but one thing I recognize is that I'm definitely going to get negative 3 from x plus 3 as a factor. I'm going to get x equals positive 3 from x minus 3 as a factor. And if x squared is equal to 0, I need you to recognize something here. This is really truly x times x equals 0, which means that either x equals 0 or, well, x equals 0. I'm not going to write this. What I'd rather write is just say that because I have the same factor twice, then I'm going to get x equals 0, and what we're going to want to write here is multiplicity of 2. And so the other thing I want to write here is no cross. It ain't going to cross at 0 because we got that answer twice. It is going to cross at these two because they had odd multiplicity. And so what I want to do is instantly, actually I would kind of just want to go put these on my graph. I get really excited when I find these. So we'd say, okay, positive 3, 0, and negative 3, these are definitely x-intercepts. So for letter C here, suppose we would want to find the y-intercept. The neat thing about this is the y-intercept, you plug in 0 for x, and I just want to remind you that you always get your constant term here, which in this case is just 0, because these two terms would drop out when we plug in 0 for their x values. So we're going to say, well, then my y-intercept is also 0. But, you know, kind of something we already knew once we knew that 0 was a 0 or an x-intercept, okay? So for letter D here, we definitely want to check for even and odd. We would say, let's do this. Let's plug in a negative x wherever we see an x. Now, showing my work, I would say, well, this is negative x to the 4th minus 9 negative x to the 2nd. But what I want you to know is whenever you plug in a negative x, the only terms that switch are terms that have an odd exponent. Both of these are even. So what you're going to see here is that we get our x to the 4th back, and this negative x squared becomes positive x squared when we square it. So we get negative 9 times a positive x squared. Hey, you guys, this is f of x. And so what we want to say is that this is an even function. And because it's an even function, we have y-axis symmetry. So the neat thing here is going to be that, well, hey, at least now when we have to go fill out a table of values, I know the left side of my graph is going to look like the right side of my graph. So in terms of what tables we should fill, what values we should fill out in our table here for x, and suppose we're calling this f of x here as our function. But in terms of what we fill in here, well, I know that my graph is only interesting in the middle here. And I'm going to go ahead and put in my end behavior before I forget, up and up. It's only going to be interesting here. Out on the edges, it's going to go up and up. So what we're going to do is we are going to plug in x values to the left of and to the right of every 0, which in this case are negative 4 and negative 2 around our negative 3. We would want to plug in a negative 1 here, but also a positive 1. And then also we would have a positive 3 and a positive 2 and a positive 4. But the neat thing about this is we're going to see that we get similar output values on each part of our graph here because we have this y-axis symmetry. So let's start by plugging in negative 4. And the way I would do this is, of course, I would get my calculator out. And I would just say, hey, you know, it's not cheating. It's just taking advantage of your resources here. So we have negative 4 to the 4th power here. And that would be minus 9 negative 4. Okay, negative 4 to the 2nd power. So I'm going to hit enter here and I get 112. Wow. 112, are you kidding me? Well, okay, we'll put 112 on there. When I go back into my calculator now, I'm going to hit second enter. What I mean by even function is remember that because we have all even exponents, it's not going to matter if I were to plug in a positive 4 or a negative 4 in here, because if I were to raise it to the 4th and to the 2nd, it's going to be positive no matter how you look at it, so we get 112. So again, the neat thing about this is because I know this is an even function and I have y-axis symmetry, the left and the right side are going to look the same. So let's try negative 2 here. Actually, I'm just going to do 1 and 2 and fill out these now that I know that. We'll hit second enter. I'll go back and I'll switch these from a 4 to a 1. And I'll have you hit enter. So we get a negative 8. And because I know this is an even function, I know I get that here as well. And if we were to plug in now a 2, we'll hit second, enter. We'll go back and switch these over to 2's. So we get 2. There we go. 2. So we get negative 20. All right, so here's the deal. A little bit different from our last graph, I noticed, whoa, okay. So here's the deal. I'm not going to be able to fit these reasonably on my graph. Looking at the fact that the other two go through like negative 8 and negative 20, I could probably fit those on there if I went by 2's on my y-axis, okay? So we're going to admit that I can't fit these 2 points on the graph. Do I still need to find their ordered pairs? Yes. We need to know how our graph is going to behave as we get really close to an x value of 4. So what we're going to do is we're going to switch our scale on our y-axis here. This time I'm going to cheat a little bit. I'm going to say that this is 10. I'll just say that this is 20 right here. And instead of saying that my scale is one thing or another off on the side, I'll just write this here. And so graphing these in, we would say negative 2, negative 20. Well, I'd go left 2, and I'd actually have to go all the way down to the bottom shelf here. And I know that because of my y-axis symmetry, I have this point here as well. But positive 1 and negative 1 both went to a height of negative 8, so these are right here. So how could we imagine a graph that at negative 4 is at 112 that would be clear up here, okay? Well, we would have to imagine that because we rise on the left, we're really just coming in extremely steeply. And that's exactly what's happening. And so we come down here, we run down here, and I would have to come back up, and here's the thing. Because we got 0 twice, or an even number of times, we're not going to cross the 0. That would mean that it would have to touch and turn around, come back down again here, and then come back up again. Let's see if I can make this a little bit cleaner. Kind of hard to do on a computer tablet. But anyways, okay, so we get this polynomial function right here, which have perfect symmetry in a perfect world. So remember, when you graph these, all we're really doing is find end behavior, find where it hits the x-axis, find where it hits the y-axis, and we're going to go plug in some extra points, and testing for symmetry, that's just a smart thing to do. Cheers.